Okay, so this is our titration calculation. So what we've done is we performed 3 titrations, and from the 3 titrations, to get a average volume, you need to make sure that your values are plus minus 1 cubed centimeters, or maybe 1 or 2, maybe 1 or 2 from one another. But to make it as accurate as possible, I would go with 1. Okay, so we recorded the initial volumes for them, and then also the final volumes that we have titrated. And to work out the change in volume, remember it's the final volume minus the initial volume. And to get the average, you add all of these up, and then you divide it by 3 to get your average volume that you required. So if I just quickly go back to your Burette, so remember you started with a initial volume and you performed your titration, and the amount of acid, because remember in here we had hydrochloric acid and in here we had sodium hydroxide, so the amount of acid that we required to neutralize the sodium hydroxide was 31.50 cube centimeter on average. Okay, so now I'm going to show you the titration calculation. So before you start analyzing your data, it's always important to just look at what are you actually doing and what is the balanced reaction equation. So you have sodium hydroxide, which is a solution, and to that you added hydrochloric acid that was in your burette. And remember, when you add an acid together with a base, you get a salt forming, and in this case the salt is sodium chloride, which is also a solution because we haven't evaporated the water off yet. Okay, so now that's your balanced reaction equation. And something that's very important to note here is the stoichiometry. So you can see the stoichiometry or mole ratio is 1:1. How do you know that? If you look at what is in front of the molecule, it's just a 1, and that's also a 1. If this was a 2, then it would have been 1 is 2, 2, but it's 1, 2, 1. So you know that you don't have to worry about that. Then let's look at what other data we have. So we know that in my Erlenmeyer flask that I have 25 cube centimeters, and the concentration is 2 moles per cube decimeters. Okay, that was my standard solution. So with this information, you can now go and work out the moles of your sodium hydroxide. So let's quickly just look at this formula here that says the concentration is equal to the moles divided by the volume. So I want to know what is the moles. You know what is the concentration, and you also know what is the volume. So let's quickly calculate the moles of sodium hydroxide. Okay, so that's going to be C times V. So that's 2 mole per cube decimeters. And the volume, now this is important because that's in cube decimeters. You need to convert this also to cube decimeters. So you're going to divide it by 1,000. And then if you calculate your moles, you will get 0.05. Alright, so now you know the moles of your sodium hydroxide. Now what we can do now is do a molar ratio. So the moles of this is 0.05. And because the ratio of sodium hydroxide to hydrochloric acid is 1:1, the moles of hydrochloric acid is also going to be 0.05 moles. Now remember, the whole purpose of this titration is to go and calculate what is the concentration of your hydrochloric acid. So now you have the moles of hydrochloric acid. But what we need to do now is actually calculate the concentration. So the concentration of your hydrochloric acid is the moles divided by the volume. So you have the moles, and do you have the volume? Yes, you do. Remember, that's the volume that we require to neutralize your sodium hydroxide, and that was 31.50 cubed centimeters. So you just need to now also convert that. Okay, so 0.05 moles, and we are going to divide that by 31.50 cubed centimeters, but divided by 1,000 to get it in cubed decimeters. So I'm just going to quickly grab my calculator. 0.05 divided by that, and that's going to give me a concentration of 1.587 moles per cubed decimeter. Alright,